When we hear the sound of an electric guitar, we often think of music, emotions, and creativity. But behind every note is mathematics at work. Calculus, for instance. Calculus helps explain how a guitar string vibrates and what formulas are being created as its string vibrates. Good day, everyone, or good evening. My name is Mario Jr. of Villarta, and I am the presenter for today's topic entitled Calculus and the Electric Guitar. If you pluck a guitar string, for instance, the string displacement, which is represented by y, plainly depends not only on time, which is the t, but on the distance, the x. This one, as you can see, this is the y, which is the displacement of the string, and the x, the distance of the string, this one, the distance it travels. So y is a function of two variables, the time and the distance, which is the x. And a more sophisticated form of calculus is therefore needed involving things called the partial derivatives. So what is partial derivatives, by the way? A partial derivative measures how a function of two or more variables that change with respect to one variable at a time, while keeping the other variables constant. So meaning, there are two or more variables that change with respect to one variable at a time, then another variable is also a constant. For example, the temperature. Temperature depends on the location and the time. Also, driving a car. In driving a car, the fuel consumption depends on the speed, the road slope, and the weight. So those are an example of partial derivatives in real life setting. Now, in partial derivatives, there are different general formulas. So for example, the function of two variables, so the formula is this one, or yeah, and then the partial derivative with respect to x, this one, and also partial derivative with respect to y is this one. This example represents the two functions, x and y. Function of xy equals x squared y plus 3y. We're going to solve the partial derivatives with respect to x. If we're going to solve that one using the differentiation, partial derivatives, the result will become 2xy. And for the partial derivative with respect to y, the result will become x squared plus 3. Now going back to the guitar string, as I mentioned earlier, the guitar string, its string, which is the y, depends not only on time, but also on the distance, which is the x. Thus, it follows the equation with the formation of the partial derivatives, this one. In similar way, the partial derivative of y with respect to x is the rate of change of y with x at a fixed time, so that it represents the slope of the string at that particular moment, as if we are taking a snapshot of the string. The first of this is simply the rate of change of y with t at a fixed value of x, and it is therefore the vibration velocity of string at that particular point. Now let's move on to the wave equation, this one. Suppose then that a guitar string has tension, which is the T, this one, and a mass per unit length, represented by a small p, this one. It turns out that the displacement y is governed by a partial differentiation equation. So this one, the equation of the partial differentiation that comes from the wave of the string. Now this one, in this part, it is the acceleration of a small bit of the string, and the right side, or the right hand side, is the force per unit mass causing it. To see why that force takes the form that it does, imagine taking a snapshot of that small bit of string, and this one. If we're going to zoom that one, zoom in, if the second partial derivative of y with respect to x is greater than 0, then the slope of the string is increasing with x at the moment. So, pa-increase. So that particular bit of the string curves slightly upward, as you can see in the figure 85. Now the upward pull from the right hand portion of the string is then slightly greater than the downward pull from the left hand portion, resulting in a net force upward either in the positive y direction. In short, it is the curvature of the little bit of the string that gives rise to the net force that we see in the particular differentiation equation. That equation itself known as the wave equation, and it was first derived and solved by Jean-Louis Rond d'Alembert, I don't know how to pronounce this one, in 1747. And the most striking feature of his solution is that it involves traveling waves. As you can see in figure 86, this one, the traveling waves. These are disturbances which travel along the string in the x direction. Moreover, the speed at which they travel is written in this formula, the square root of t over the length, or the time and the length it travel. So the greater the tension in the string, the faster they go. In fact, they travel so fast on a guitar string that it's almost impossible to see them, but they can be seen quite clearly on a slack wash. Now let's move on to the vibrating strings. Suppose then that the string is of length L and extend between x equals 0 and x equals L, where it is fixed so that y equals 0 there. The simple solution of the partial differentiation equation is this one. Then turns out to be of the form y equals a sine pi times x over L cos wt, where the w is a constant. The equation y equals a sine pi times x over L cos wt represents the standing wave, the normal mode of vibration of a string of length L that is fixed at both ends. It is derived from the one-dimensional wave equation by solving a boundary value problem. The whole string therefore vibrates with a single period, 2 pi over w, but different parts of the string corresponding to different values of x vibrate by different amounts. In particular, y is always 0 at the two ends. This one, y is always equals to 0 at the two ends, x equals 0 and x equals L, as required because sine 0 is equals to sine pi is equals to 0. Why this matters for vibrations? This is because using 0 and L makes the wave equation solution clean, so the string automatically stays fixed at both ends. And the frequency of this mode, either the number of vibrations per unit, is this one. For any particular guitar string, the tension T and the density, the P, tend to be fixed. So the feature of most interest here is that the vibration frequency is proportional to 1 per L. This is why pressing down on a fret and therefore shortening the string produces a higher note. The vibration frequency of each mode is whole number multiple, represented by n of the fundamental frequency. Again, this emerges from the differential equation itself. This is because for these higher modes, y is proportional to sine n times pi times x all over L. And this is only 0 at the right hand and the x equals L. if n is a whole number. In particular, the n equals to this one mode in which the two halves of the string move in opposite direction at any given moment, vibrates at twice the frequency of the fundamental and therefore sounds an octave higher. And while the fundamental n equals 1 tends to dominate, it is possible to give more emphasis to the higher harmonics by plucking the string near to an end. And this is why the resulting note then sounds harsher and less well-rounded. In addition, there are various more sophisticated playing techniques well known to rock guitarists for suppressing some modes of vibration and highlighting others. And several of these tricks exploit the fact that the higher modes have nodes or point of no motion at select places along the string. Often, then it is by artificially creating a suitable node that you get the particular mode you want. In conclusion, when we pluck the string, it vibrates. The height of the string at any point depends on both time and position along the string. This is where partial derivatives come in. They help us understand how the string changes if we focus on, just one variable at a time, like time or position. Mathematically, we use the wave equation. It predicts how the string moves and vibrates over time. This vibration produces sound waves that reach our ears. The engineers and musicians use these equations to design guitars that sound better, sustain longer, or even create new tones electronically. So, next time when you hear an electric guitar, remember, everything riff or gentle melody is not just an art. It also the math in motion. The calculus explains it and physically brings it to life. So that ends my discussion or my report. Thank you for listening and God bless us all. Thank you so much.